Assalamualaikum warahmatullahi wabarakatuh. Good morning and welcome to the General Assembly, the 11th International Conference on Sustainable Agriculture and Environment 2024. My name is Dendra Shirley, and it is such an honor for me to be your Master of Ceremony in this event. On this occasion, I also would like to greet and welcome Her Excellency Professor Dr. Fitria Rahmawati, Vice Rector of Academic Students Affairs of Universitas 11 Maret, and welcome to Her Excellency the Honorable Head of Institute of Research and Community Service of Universitas 11 Maret, Profesor Dr. I Gusti Ayu Ketut Rahmi Handayani. And also, we welcome all the international speakers today, Professor Ahmad Yunus, Rodayos PhD, and Professor Sanjeev Kumar Panda, and Professor Heri Utomo. Ladies and gentlemen, on behalf of the committee, we are grateful to be blessed with health and opportunity in this international event, which can bring us together, academia, researchers, and practitioners who are responsible for delivering sustainable agriculture and environment. This event is hosted by the Research and Development Center for Biotechnology and Biodiversity, Universitas 11 Maret, Indonesia, as a forum to exchange cutting-edge research, innovative practice, and visionary ideas that aim to foster a harmonious plan between agriculture development and ecological balance. Ladies and gentlemen, before we start, please allow me to read the agenda for today. First agenda is singing national anthem Indonesia Raya. And then following with the welcoming speech and opening remarks. And the main agenda is listening to the presentation from our distinguished experts, following with questions and discussion. And the last agenda is closing. Ladies and gentlemen, for a brief moment, we would like to invite you to sing our national anthem, Indonesia Raya. For the participants, please prepare.
Tanah airku, tanah tumpah darahku. Di sanalah aku berdiri, jadi pandu ibu. Indonesia kebangsaanku, bangsa dan tanah airku. Marilah kita bersatu, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya.
You may be seated now. Ladies and gentlemen, we are moving on to the second sessions of welcoming speech by the... Ladies and gentlemen, we are moving on the second session of welcoming speech by the head of the Institute of Research and Community Service of Universitas 11 Maret, the Honorable Professor Dr. I Gusti Ayu Ketut Rahmi Handayani. The time is yours.
Good morning, all speakers, distinguished guests, esteemed colleagues, researchers, and all participants. It's my great honor and privilege to welcome you to the 11th International Conference on Sustainable Agriculture and Environment. As the head of the Institute of Research and Community Services, Universitas 11 Maret, especially proud to see the efforts of the Center of Biotechnology and Biodiversity Research and Development in organizing these important events. This conference brings together experts, innovators, and thought leaders from across the globe, uniting us in the common goals of tackling some of the most pressing challenges of our time. Sustainable agriculture and environmental preservation are essential not just for today, but for the well-being of future generations. The issues we will address ranging from sustainable agriculture practices to biodiversity conservation, climate adaptation, and cutting-edge biotechnology are pivotal to shaping a future where both humanity and nature thrive. The Center for Biotechnology and Biodiversity Research and Development is pivotal in advancing research that intersects agriculture, biodiversity, and environmental sustainability. I'm delighted to see the Center's contributions reflected in this conference, which serves as a platform for exchanging ideas, solutions, and innovations that will drive us toward a more sustainable and resilient global ecosystem. In this conference, we will engage with leading experts, participate in stimulating discussions, and explore pioneering research that can transform agricultural practices and environmental strategies. The diverse presentations and workshops offer not only deep insight, but also opportunities for collaboration and partnerships, enabling us to push the boundaries of sustainable innovation collectively. I extend my heartfelt thanks to the organizing committee, our distinguished speakers, all participants for your commitment to this cause. As we begin this exciting journey of learning and collaboration, I encourage you all to actively participate, exchange ideas, and think critically about how we can together build a future where agriculture and the environment are harmonized in a sustainable way. Once again, welcome to the 11th International Conference on Sustainable Agriculture and Environment, organized by our dedicated Biotechnology and Biodiversity Research and Development Center, Universitas 11 Maret. I look forward to the inspiring discussions and insights that will emerge from this gathering. Thank you so much, and I wish you all a fruitful and rewarding conference.
Thank you, Professor Dr. Igusti Ayu, for the welcoming speech. Ladies and gentlemen, the next agenda is opening remark from Vice Director for Academic and Students Affairs of Universitas 11 Maret. For Professor Dr. Fitria Rahmawati, the time is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. The Honorable Head of Center for Biotechnology and Biodiversity Research and Development, the Honorable Conference Committee, and all of the participants. Praise be to Allah Subhanahu wa Ta'ala who giving us a good and healthy condition. Then we can attend this conference, the 11th International Conference on Sustainable Agriculture and Environment. The conference, which is organized by Center for Biotechnology and Biodiversity Research and Development, a center in Universitas 11 Maret that commit to advance knowledge and innovation in agriculture, biodiversity, and environmental sustainability. The importance of sustainable agriculture and environment cannot be overstated in a world that faces increasing challenges related to climate change, food security, and environmental degradation. This conference provides a platform for researchers, academic, practitioners, and policymakers to come together to discuss, to collaborate, and create solutions that will have a lasting impact on the future of our planet. This year's conference promises to be special, to be impactful, with a diverse array of topics addressing cutting-edge research, technological innovation, and policy framework that can be drive the transformation we need in agriculture and environmental protection. Integrating biotechnology, biodiversity conservation, and sustainable practices will be at the heart of this discussion. I would like to express my appreciation to the organizing committee for their hard work preparing this conference very well, and to all of the speakers that commit to conduct research and discuss their research in this field. Your commitment in sustainable agriculture and environment will help us to navigate the complex challenges that lie ahead. I hope all of the participants will actively involve in this conference, initiate collaboration, exploring new ideas, and pushing the boundaries of research in ways that will benefit not only for our communities, but also for the world. Finally, on behalf of Universitas 11 Maret, I welcome you once again to this
Conference on Sustainable Agriculture and Environment. Ladies and gentlemen, now we have come to the main agenda, the seminar session. The speaker is Professor Yunus from Universitas 11 Maret, Indonesia. Also, our speaker is Mr. Rodayas, PhD from Institute for Bioeconomy and Agri-Technology. The presentation and discussion will be moderated by our moderator, Ms. Rufida Maulina, Master of Science. But before we begin, allow me to read her short biography. Ms. Rufida Maulina, she is a lecturer and a researcher in midwifery study program in a medical faculty. Okay, so she was studied Masters of Science in Nurse Midwifery in National Taipei University of Nursing and Health Sciences. So, without further ado, please welcome our moderator, Ms. Rufida Maulina. The time is yours. Before we present our moderator, we would like you to see videos.
The world faces a significant global challenge as the human population is projected to reach 9 billion by 2050. Food security ranks among the most urgent international issues. The COVID-19 pandemic has further strained health systems worldwide. Fossil fuels, predominant in electricity production, emit greenhouse gases that exacerbate climate change. The last decade has been the warmest ever recorded, leading to devastating climate disasters. It is necessary to accelerate the transition to an affordable, reliable, and sustainable energy system by investing in renewable energy and implementing environmentally friendly energy technologies. Universities are pivotal in advancing global welfare. Universitas Sebelas Maret, as a higher education institution, has become the common thread holding together all solutions for the 17 Sustainable Development Goals through its learning, research, and community service programs. Universitas Sebelas Maret was established on March 11, 1976, as one of the most outstanding universities in Indonesia. Universitas Sebelas Maret has built its vision and strategic plan on becoming an internationally excellent center of development in science, technology, and arts based on the noble values of national culture. Universitas Sebelas Maret is located in the city of Surakarta and is also known as Solo. Solo is a very comfortable city where Javanese culture and modern life blend. The Solo life, which upholds the value of harmony, has prepared Universitas Sebelas Maret graduates to be future leaders. To achieve the vision of Indonesian higher education, Universitas Sebelas Maret offers a variety of courses on a wide range of subjects conducted by 14 faculties, a vocational school, and a graduate school. With its adequate and appropriate learning infrastructure, Universitas Sebelas Maret offers a unique and engaging learning environment. It provides integrated IT facilities and information systems in a convenient academic atmosphere and green campus area. In addition to being a center of excellence, Universitas Sebelas Maret is home to students from all 38 provinces in Indonesia and 34 countries worldwide. This campus life creates a multicultural environment that promotes mutual understanding. Embracing diversity and respecting all cultures makes every student feel recognized and valued.
We understand that the world is facing many problems nowadays and also challenges in the future. Therefore, Universitas 11 Maret present to the society for solving the problems and anticipating the future challenges by three main activities: research, education, and community services. The significant contribution of Universitas 11 Maret is not only in national level, but also international level. Our excellent result in the international
Alright, after we saw videos from Universitas 11 Maret profile, we would love to see our lovely moderator, Miss Rufidah Maulina. The time is yours.
I'm Rufidah Maulina, and I'm honored to be your moderator for today. Good morning, ladies and gentlemen, and welcome to our international webinar on the 11th International Conference of Sustainable and Agriculture and Environment 2024. We have an exciting program ahead featuring two distinguished speakers who will share their groundbreaking research on optimizing agriculture through innovative approach. Before we begin, I'd like to quickly go over the structure of today's session. So each of our speakers will present for about 45 minutes and Q&A session after two speakers delivering their speech by 15 minutes Q&A. And feel free to raise your hands and unmute your microphone. Submit your question in the chat box throughout the session in the Zoom chat box or in the live session. We'll do our best to cover as many as possible questions. So ladies and gentlemen, before we begin, let me introduce our speaker. Our first speaker is Professor Ahmad Yunus from Universitas 11 Maret, Indonesia. Professor Yunus is a renowned researcher in the fields of plant physiology and plant technology. His work has contributed significantly to understanding how plants respond to various environmental factors and the development of new technologies to enhance crop resilience and productivity. His latest work was evaluating the phenotypic responses of CRISPR Cas9 in mentik wangi rice and clinical effect of Echinacea purpurea as an antiviral and effects on reproductive hormones. Without further ado, let me invite our first speaker, Professor Ahmad Yunus, to share his insights. Good morning, Professor Yunus.
Oh, good morning.
Good morning, Professor Yunus. It's a pleasure to have you with us today.
Yeah, okay, I'm fine. And so we can, yeah, okay.
Before we dive into the presentation, I would like to remind you that you have 5 minutes to deliver your speech, and the question and answer session will be delivered after 2 speakers. So, Professor Ahmad Yunus, the floor is yours.
Okay, thank you, Mrs. Moderator. I will try to present and share my PPT. Okay, we will presentation about our research group in this our laboratory with the researcher from BRIN Cipinang Bogor. The title is The Assembly of Aromatic Rice on Early Maturity, Short-Term, High Yield, and Resistant to Bacterial Leaf Blight Disease through the DNA technology. This technology, as I think, this is the frontier technology for the biotechnology. Our research roadmap is we have the founded from the LPDP by the scheme RISPRO productive, yeah, from the LPDP, and we give the 3 years for funding for research, and the target of research in 2025, if we have to obtain a new variety of aromatic rice, mentek susu, and mentek wangi with the qualified trait like the early maturity, short the stem, and resistant to blight disease. The activity in the first year or year 1 is we done the construction of CRISPR-Cas9, and after that we introduce CRISPR-Cas9 plus into the rice plant, and the third activity is molecular analysis to the mutant rice. The activity 1, we construct the CRISPR-Cas9 expression to the plasmid. We elect or select the P direct 25H and P direct 21A is from the reference Cermak et al. 2017. This is our plasmid to make the construct. And to design the guide RNA, we use the CRISPR tool, CRISPR-T4.net, to help us to design the guide RNA for the 5 gene. Yeah, gene in the left low, SD1, small dog one, D, heading did, yeah, and GA, gibberellin gene, and GKX. So the design of spacer guide RNA, we selected the sequence target for GA20, GA20, Orija sativa GKX. GKX is cytokinin, and heading did, yeah, headed 2, headed 2, headed 1 and 2, and Orija sativa sweet 11 and sweet 14. This is for the bacterial blight resistant. The reverse complement, yeah, the right side and the left side is the sequence for G guide RNA spacer from 5 to 3. And we found the primer design for guide RNA for 4 gene. This is the multi sequence of guide RNA that we use to the assembly of the plasmid construct for the CRISPR and Cas9. This is the picture of the Cas9 plasmid construction for the plasmid direct 25H. One is multiple guide RNA. Yeah, there is consists of 6 or 4 guide RNA. Second is 2 guide RNA. That is for gen GKX and gen and the third is a single guide RNA for heading did, yeah, Orija sativa heading did guide and guide 2. This is the diagram of the P direct. The red color is Cas9, and we need to more intense to the arrow, blue arrow. That there is the CCDP. That CCDP is our important attention. So this is the result: multiple construction of guide RNA. Yeah, R1 is fragment promoter and guide RNA1. R2 is fragment gRNA2 spacer, and etc. until R6, yeah, fragment guide RNA7 spacer. This is according to the, we have the 6 or 7 construct. And after that, we transform to the Escherichia coli. This is the picture, the result of transformation to E. coli. Yeah, ABC, the A6 guide RNA, B is for guide RNA, and CN, I think, is single guide RNA. And after we select and PCR for the colony, we found several colony. They have the construct that we want to be. Yeah. And after that, we do sequencing for the colony that have the positive code. But unfortunately, the colony is not like this, not like adjacent to the plasmid. So we have to try to improve the purification or to order the other prime. And also we need to digest plasmid direct, this plasmid direct with endoplasmic restriction enzyme PAN1 to remove the CDP sequence and reamplification again with the new primer. The construction of two guide RNA, yeah, this is the result, yeah, after the purification, and we do the further reaction by Golden reaction and transformation to E. coli again. We have some colony that show the positive result. So the construction result of two guide RNA in P direct 25, yeah, the left picture is for CKX or cytokinin, and right side is for sweet, and they have some color. The red color is guide RNA sweet 7 and 14, yeah, and blue is a blue color is CKX guide RNA, yeah. Also, this result show that the P direct 21A, yeah, for guide RNA gene edited. Edited is early maturity, and edited 1 and edited guide 2. Yeah, this we have the perfect the results. And in the activity 1, we already construct for the plasmid that are ready to transform to the embryo or callus of rice. For the plasmid PY20 or PA20, this is the done by together with Mr. Santoso from BRIN, and others is have done by our student, PhD student in program Doctor Agriculture in UNS. Yeah, and we have some construction, and this I think this gene is very important to rice, and maybe we can try to another rice if we want to have the early maturity, resistant to blight, and also the have high production. This gene we have and already constructed. The activity 2 is introduction. Yeah, after we have construct to callus or embryo. This is the construct 1, 2, 3, 4, 5 we have already, and transfer to callus of rice. And after we study the regeneration of mentik wangi and mentik susu for two kind of explant, yeah, mature embryo and immature embryo. The result is show that the mature embryo is uh, cannot be applied for transformation. Yeah, we have the experience for fail and fail. And we switch to the expand from immature embryo. After, if we do the transformation with or the source from the immature embryo, we can successful for transformation, but no, not all the colors is successful. So the presentation is if we transfer to the media with antibiotic, so only 2% they can grow, and without antibiotic we can grow until 80%. This is our difficulty to the differentiation or organogenesis from callus to plantlet. And also for another callus, yeah, we have the successfully only 8% with antibiotic, and without antibiotic we have the successfully until 91%. Maybe some audience who have experience to regeneration of callus from rice, yeah, so please let me know. This is the transformation into the mentik wangi, yeah. So this picture is really a picture, and this is still in the laboratory of biotechnology in PP Biokin in Bogor, because at this time, yeah, COVID 2020, 21, 22, we don't have construct the laboratorium in the Faculty of Agriculture UNS, but start from 2023, we already construct the laboratory for the DNA editing in UNS. The result is the transformation, the first, second, the third. So the putative mutant, the successfully only several mutant, but we already found this mutant putative, 30, the plantlet, and also for the mentik wangi, for the gene suite, for the resistant to bacterial life blight, we have we done the transformation 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So we have all totally is 159 mutant putative of mentik wangi, yeah. And also for the gene DR20, ICSAE-X, and sweet and heading dip, also we have we done transformation 1, 2, 3, and we have the 30 rice putative mutant. Yeah, and also for mentik susu, the same technology and methods we done to the mentik susu. This is the picture, yeah, and after the selection in the petri dish for the colors differentiation, and at the same situation for mentik wangi and mentik susu, we have only several putative mutant of mentik susu for GA20 and sweet, and also for ICSAE-X and heading dip, gene. We have several the mutant of mente susu. And also for GA20 suite and GKX and HDX, yeah, this is better than another transformation. We have in the total 157 putative mutant T0, yeah, from T susu. The result of activity 2, yeah, for the wangi, we have the putative 30, yeah, mentik wangi transforman, and 159 mentik wangi transforman with sweet construct, and 30 mentik wangi transforman with CKX, GA20, sweet, and HD. So this is the one in the one mutant, they have the 4 gene. Yeah. For susu, we have 53 mentik susu transforman with GA20 and sweet, and 24 mentik susu with construct CKX and HDX. Yeah. Dua. And 157, we have the contract for 4 gene. And after that, we check the sequencing to correct this is the really mutant or not, yeah, the sequencing. So after we sequence for the putative mutant, we have the after the PCR, yeah, after the PCR, we take the result of this PCR for this gene, for example, gene GA20, GKX, sweet, and HD, yeah. We sequence for several mutant, and for example, for mentik wangi, for in CKX, yeah, from the several mutant, we obtain 2 jalur, yeah, 2 line, yeah. That is the 1 insertion and 2 substitution, and also for like MV 7.1 and MV 20.1. We have the 1 insertion and 2 substitution. This is no mutation. This means that the sequence is the same with the wild type for the mentik wangi. Also for the GA20, yeah, we have 2 mutant, MV 6.2 and 3 mutant, MV 10.3 and MV 11.2. For MV 6.2 is 1 substitution. Also MV 10.3 1 substitution, and MV 11.2 is also 1 substitution. Yeah, and for the sweet also we have 2 mutant, MV sweet 11.113 and 121. This is the mutation is 1 substitution and also 1 substitution compared the sequence of wild type of mentik wangi. And also for sweet, this other line, yeah, also 1 mutant with 1 substitution of the nucleotide. And yeah, this is also, yeah, this mutant we really we have to some many, yeah, maybe hundreds mutant must be sequencing, but this is the limitation for the budget. And also for Mente Susu, we try to sequencing after we done the PCR of the positive colony, positive planet. Yeah, after this, yeah, we also do the sequence for four gene. Yeah, like this. The sequence for the GR20. Yeah, we have for the several mutant with one substitution, MSGRC 100.1. Yeah, and also this is the others. Yeah, MKAC 173. There is the substitution for one nucleotide. And for the suite 11, we have 3 mutation. Yeah, the mutation is a substitution one base, one nucleotide. Yeah, yeah. So for the several line. For the conclusion, yeah, the construction activity obtained for the construct, yeah, construct for CKX, construct for suite, construct for heading did one, guide one, and heading did guide two. This contract in transform into agrobacterium and sent to transformation into minyak wangi the susu. The transportation activity, yeah, 15 minyak wangi the now the 0 28 minyak wangi positive carrying sweet 11 and 14. 36 minyak susu is carrying KA and JKX, also 64 carrying Cas9 Oriza sativa. And mutation in Mentekwangi line, yeah, we have 3 line for the KA20, 2 line for JKX, and 5 line for Sweet 11. And in Mentek Susu, we have 2 line mutation for KA20 and 3 line mutation for JKX. Yeah. This is the application for our student. Yeah. Yeah, we also thanks for all our team researcher, Prof. Edi, Prof. Samanuti, Dr. Muji, Dr. Viko, yeah, this is our student, Andriana, and Dr. Joko Santoso, who Dr. Admitri, and who anniversary is from BRIN Cipinong, Bogor. Thank you very much.
Okay. Thank you for your valuable insight, Professor. Very clear presentation about the step of your lab's research. So, conducting research in order to fulfill the rice demand as staple food in Indonesia. So, Professor Yunus and with collaboration with BRIN have done amazing work to help meet the demand for rice, key food for many Indonesian people. By using gen editing technology, they've created a type of rice that not only has better quality, but also smells great. It's an exciting step forward in the world of food science, Professor. So we hope that with this idea, in the future, we may be able to export your research to other countries. So before we move to the questions, I would like to ask one question, Professor. So what inspired you to focus on this field, and what hope that you want to achieve in the future of your research?
Yeah, okay. Yeah, our countries, through the department or the Ministry of Agriculture, state that in the next future, we have to increase the production of food, especially as rice, because according to the Bureau Pusat Statistik, our consumption is increased year by year. In the 2024-25 is about 22 million tons of rice is need for our population in Indonesia. So the target, this target is must, the meaning is must be all the researcher in the university or in the research center must be increase the production of rice. Yeah, the rice is must be adaptable to the uh, extreme climate change, extreme of the environment, and also the rice must be have a short life cycle. That's mean the rice is must be the early maturation maturity. So the for this purposes, the technology we have done is by the DNA editing. This DNA editing is the frontier technology for biotechnology. I think this our work is can, yeah, we hope can support our government program to swasembada pangan. Yeah, thank you.
All right, thank you, Professor. So maybe some of the respondents or the participants want to ask some question, you can chat in the chat box. You can text chat box or you can raise your hand in the Zoom meeting and unmute your microphone. Okay, if there is no one question to Professor Yunus, maybe I want to ask some more question, Professor. So with this climate change, maybe in the future we will have some challenges regarding our staple food. So do you think, Professor, that because of the climate change in Indonesia, the staple food will change from rice to maybe grains or some other food, Professor?
No, yeah. Yeah, of course. For the climate change anticipation, we need, yeah, for all the breeder or scientists, especially in the agriculture and animal husbandry. So we need to more focusing the priority of research, because our uh, productivity of food, especially in rice, is very low and compare with the production of rice in China. So this is our intention for the rice, because we really we have the enough of the genetic diversity of rice in Indonesia, but we don't we don't, we don't have the some breeder or the scientific to create or engineer the rice to blow up to increase the production. Yeah.
Okay, thank you so much, Professor, for your insights. And we hope that in the future, because even
There's climate change happening in Indonesia,
on
it's
change
all
acceptable those
law.
advice, and I think that if I become Indonesian and want to change with noodle every day or other grains, it may be difficult for us. So thank you so much, Professor, for your valuable insight. And we next move to the second speaker. So our second speaker is Efthymios Rhodias, PhD, from the University of Turin, Italy. Dr. Rhodias specializes in optimization of researches in agriculture and the agri-food sector. His research focuses on sustainable practices to maximize efficiency in agricultural production while minimizing environmental impact. His primary experience and research, including among others operation data management in agricultural processes.
Hello everybody, my name is Efthymios Rhodias. I am from Greece and I am the presenter of this session. Unfortunately, I will not be able to physically be present in the conference, so I will share now my screen and start my presentation. Now you can see my screen. I have worked many years after and before my PhD in CERT, Center for Research and Technology in Greece, and this research center has 5 institutes below it. So one of it is this that I present you now, the Institute for Bioeconomy and Technology. I will now give you a very glance of their page. This is the main web page. The main philosophy of this and the main domains of this institute is the agri-intelligence, energy and sustainability and economics and biomechanics. You may, I'm sorry, visit your by yourself also the website. We have worked in many national and European projects and we have published many publications on this. So now we start my presentation. The presentation has to do with, excuse me a minute. Okay. So now probably you can see my screen about advances in precision agriculture towards minimization of environmental impact in crop production systems. And I will start with giving you some insights about that. So the challenges that we have to face in agriculture are related to global food security. So as years and decades passing, the global demand for food is getting higher and higher because of the population increase. And we have many changes as well in the global demographics and also in national and European and globally level. There is a swift towards meat consumption. There are many trends towards veganism or vegetarians or other food preferences in more and more in developing countries, more and less in developed. And in parallel with the higher food demand, we have also the degradation of natural resources. This is the first, let's say, challenge that we have to face in agriculture. Going further is the sustainable management of natural resources. This in this graph, you can see the four main natural resources, that is the soil, the water, the air, and the biodiversity. As for the soil, let's give you a brief demonstration of these natural resources. As for the soil, we have a very a real challenge to face with the erosion, the soil compaction, the salinization, the soil biodiversity, and the sealing. So we have some significant problems with related to the soil. Regarding the water, we have 20% of the surface water that is very seriously risk from pollution. Let's give you a few more examples. 6% of European cities are overexploiting their groundwater resources. 50% of wetlands are endangered, and demand for water is always growing and continues growing. Biodiversity loss will reduce nature's ability to maintain ecosystem services such as water filtration, etc. And the air is related to ammonia exclusion, to methane and nitrous oxides. Another challenge is related to energy consumption. Energy consumption is highly related to environmental impact at any level, but also in agriculture. We have here some facts. These are that worldwidely, energy demand is projected to grow by 44% from 2006 to 2030. Probably this number has already been achieved by now, but we can keep this 44% by 2030. In 2030, the energy imports of EU will be up to 70% of the energy needs. So EU will be and is highly dependent on fossil energy from other non-European countries. These are the facts for EU. As for food safety, the EU integrated approach to food safety focuses on high level of food safety, animal health, of course, animal welfare, and plant health. This is going to be phased, is going to be assured through systematic farm-to-fork measures and adequate monitoring at any level of crop production and animal production. So we have also the climate change. And here you can see the impact of agriculture that is related to CO2 accounts, to methane, to CO2 to methane. For example, 1 ton of methane has about 33 times the warming effect of 1 ton of CO2. And agriculture is a significant source of methane. Of course, that's a real fact. But also we have the impact on agriculture. The impact on agriculture is that we have new crop diseases, we have effects of productivity. On productivity, we have also water scarcity. This is the difference between the impact of agriculture and the impact on agriculture. So we have the challenges, that is, as the ones that we mentioned: global food security, sustainable resource management, energy consumption, food quality and safety, climate change, and also we have social aspects and demands. Going from the challenges to the goals, we have these goals here on the right: the increased productivity in resource use. This is one of the goals. The increased net greenhouse gas benefit per unit production. The minimization of the non-productive losses from farm to point of use. The increased control of the performance of complex systems. And also better balance of productive outputs and sustainable nature systems. These are the goals summarized here. So we have to go from the challenges that we have to face to achieve these goals. But we have some ways, some means to achieve this. From challenges to goals, we have some solutions to propose. One of the solutions is precision farming. Probably all of you have seen that some of these maps here, as you can see here or here. We will say some more things later on, but we have to going from the traditional and the traditional ways of cultivating the soil and the whole anyway to managing the whole crop production system from the traditional ways to precision farming ways and means. We have these satellite-based navigation systems. Okay, you have seen many of them that are used in the modern tractors and implements. The satellite-based navigation systems have some features. As you can see on the right, they have increased available working time. They decrease overlapped areas. They decrease non-covered areas. They support, let's say, with all these ways here, the crop production systems. Less experienced operators, we don't have to have high qualified persons to operate a machine. We have increased quality of work, we have increased operating speed and increased productivity per unit. And here you can see, let's say, how a planter row can be used under a waterway, let's say, or under or over, sorry, a waterway or over a place or an area in the field that should not be planted or should not be fertilized, for example. Now we'll show you a short video on this. As you can see, the boomer type stops and begins again, stops and begins again to spray. So this is one of the benefits that precision spraying gives us here. Let's go in deeper by using one of the past projects that I have been involved, that is called offline and online logistic planning of harvest processes. We will see that here all the compounds, all the systems, the subsystems that were involved in this case study. So we have combine harvesters, we have in-field transport systems, we have on-road transport systems, we have grain conditioning and storing, and we have also the farm manager. So all of these are collected in the centralized server. We have also data from external parties as Google, as BASF, and so on. And all of them are offline and online, modelized and optimized. Let's go in deeper. So we have some subsystems or sub data that we use here. We have data from field, location, access points, and outline of the field. We have also data from combine harvesters, position, speed, yield, and bin level. We have data from in-field transport, where is it located, how fast is it going. The on-road transport also the same. We have also conditioning and storage, where is located. So we have to optimize the goals here, less time and less soil compaction. But going further to that, we have also the topography. In order to achieve the cost goal, we have also the topography, we have also the fuel consumption, less fuel consumption, also in the combined harvesters and the transportation systems in field and on road. And also we have the drying capacity that is also directly connected to cost. And also giving another optimization goal that is yield and quality. Yield and quality, we have to use to predict yield and quality. We have to use external data as weather forecast, commodity price, and fuel costs. As for more data, we need yield estimation from the field, quality estimation, and ripeness. And also we need also grain moisture, grain quality, and here the conditioning, humidity, grain moisture, and CO2 level. So in all these, putting all this together, we can achieve these 5 optimization goals in a very certain case study, in a very certain field operation that is occurring every time that we want to harvest. Here you can see the user interface, how it's presented, how it's demonstrated here. So we have this screen. If you can see, we have selected, let's say, offline an in-field route planning that is parallel to the long side of the field. So we have parallel, we are operating parallel to this side of the field. But we have achieved to check also in offline mode. I will say that again, in offline mode, we have checked that if we cut, let's say, the field into subfields, we can achieve a better, let's say, offline route planning system, going parallel to this side and here parallel to the other side. This is very dynamic. Even if it's offline, we can check multiple scenarios, so we can decide before we operate, before we're going to harvest the grains, we can decide which side or which route planning in field we will follow. And then we're coming to the online execution. The online execution is going on the tractor, let's say. So we have the offline pre-planned as a starting point, and then we have the estimation system settings that will be replaced with the real-time data. And we based on the initial plan, will be replanned continuously as respond to the actual events. And here we check that the menu, let's say, of the screen, or what's the operator is seeing on the screen. So we have here the online execution, different menus, okay, and going deeper, just for given more details on this. Here you can see, let's say, in the red, the means manual handling, or in the green, we see the auto steering. So here's the time for the next step. This is the clock. This is the speed. This is the cubic, the tank containers, and also the meter to the next step. How many meters? So we have very specific information here. And also here you have an attention point that here should be alert, let's say, the operator. Going further to the next one, so here you can see where should be a turning. So full color means next stop. Second step here with the dust line, and then numbers for the auto steering line you have to pass. So you have to pass 3 lines to come to the next 4th one. So, and this also, all this menu can be supported by acoustic effect. Let's say from a beeper. And here you have during the next, so you're going to the headlines, or you're going to the next from line to come back to the field. Here, let's see how the combined route planning is working. So we have data from the combined harvester that's related to speed, harvested hectares and grain tank content. And we have also a back and forth data exchange that this has to do with an optimized route planning or unload place. So here we have the start going back and forth, start unloading at this time 105, stop unloading at the 107. You can see here it start unloading and stop unloading. And also we have also here we have the speed of this combined harvester and harvested area and how many grain is contained in the tank. So we will have all the data from the involved machines, from this machine here, from this tank here. They are all sent to the server. As you can see in this picture, they are sent to the server and all these are communicating each other. So we have a real world system that will create an optimized plan. And the plan is distributed into actions for each of the individual machines. So they are communicating and they create an optimized plan. And here you can see how is it presented in each one of these systems. The directions are given, leads to actions and change the real world system. These changes leads to new data and continuously replanning of the task. So we have a complete system that because a field is not just an area of land. We have fields in Spain, Kansas, for example, in Denmark and Brazil. So it's not just a land. It's a complete system. And one of the problems that we have to face in agriculture, engineering agricultural systems are the soil compaction. So we have to create a sensitive route planning in field based on minimizing soil compaction. Let's say here, if you can see in this chart, we have for a field, if we follow an A to B pattern, let's say from A side to B side, so parallel to one direction, to one side of the field, sorry, we can see how this X to Y field, how this specific areas, specific lines, let's say the specific areas of the field are over compacted. The soil is over compacted, so these are the red ones. And also here, how this affects to the electric conductivity of the soil and how this affect the soil, yes, the potential risk. Okay. So we by this slide, I want to emphasize on the soil compaction, on the necessity to face soil compaction. And for example, in this referenced work, we have some savings in these two indicative crops, barley and wheat. We have some savings in hectares, in euros per hectare, the expected and the up to savings. And let's going also here to the very, very, very well-known system of controlled traffic farming. Controlled traffic farming has a very basic principle. This is that we want to establish permanent wheel tracks, permanent tram lines that or that the tractors will move on in the field. The tractors and the implements will not move wherever they want, will not turn wherever they want in the field. They have very specific, this system of controlled traffic farming has very specific rules that if we follow them, we have to establish this, let's say 3 meter width track or 6 or 9 or whatever we want to establish, but we will establish permanently, and then permanently the tractors will move on them. What are the benefits? The benefits are summarized in these 4 bullets, let's say. The increased yield. Imagine that the tractors will not pass over every inch of the field area. Will pass only over these lines. So in all the other areas, field areas, the yield will be increased versus the traditional way. Okay, we have savings in energy, we have reduced loss of CO2, of course, and also we have reduced loss of water. Here we have a completely new system that cannot be opened now. Yes, I'm sorry, I cannot present to you. A completely new system that is presented, I think, if I remember well, in Australia. Another huge chapter of modern agriculture towards minimization of environmental impact is agri-robotics. Agri-robotics have some sub-systems, sub-components that has to do with their their communication with the control system, and they are giving them the opportunity to move and operate in the field. Here you can see some of them. So we have a GPS receiver, GPS antenna, they have the main controller, we have a wireless router, we have an obstacle detection system, we have a laser scanner, we have cameras that are going to present here, of course. Okay, visionary systems and so on. And here we will show you some grass bots, some agri robots that are used for grass management. Let's have a look on these short videos. And some more. I'm sorry. And let's see also the other one. So these robots, these grass robots, are used I'm sorry. Yes. Yes. Sorry, I stopped. Okay, now you can see that. So these robots are used to mowing and conditioning of the grass. And there are many cases that we use fleet of such robots to manage, to operate in huge grand grass areas, such as here, you can see here. So we have a robot that cuts and aligns the grass in a line, and then another robot collect and send it back to the container here. Other agri-robots that are used in other crops are related to vineyards, or related to strawberries. Here you can see strawberries harvesters, very sensitive crops, both of them. Here again in vineyards and also in apple orchards. I'm sorry for this. And let's have a look at another video here. And let's move forward. Biomass from extensive areas. Another project that we have been involved, have some subsystems that are related to the use and generally the grass operation. Here we have different scenarios: mowing, forest harvester, loading and unloading, loading container on the truck, transport and unloading here. The subsystem, the inputs that are coming into this whole process. Another scenario: mowing, baling, picking up, loading, transporting, unloading, or all of these are evaluated or assessed, let's say, in under the scope of minimum environmental impact. But also we have here the operating time, I'm sorry, under these different scenarios, and also the cost, because everything has to be evaluated also under the minimum cost, not only minimum environmental impact. Here you can see also how these different locations of these biomass factories can be assessed in order to minimizing the transporting cost. And this is the real challenge that we have. We have to follow these 5 sub-challenges, let's say: precision agriculture, specialized routing, automation and control, satellite technologies, the use of them, and decision support systems. So we have here the in-field route planning, let's say. We have also the multiple fields operations. We have also here the rural road transportation and the public road transportation. So we have an input-output flows, material flows, logistics in-field, inter-field, inter-sector logistics, and inter-regional logistics. And the goal is this one. Now we are here today, let's say, we have this environmental impact, we have this yield, but we have to achieve less impact with higher yield. That's why we used these technologies, these smart farming tools. That was my presentation. Thank you very much, everybody, for listening to me. And I really wish I could be online with you, but I'm really sorry that I will not be able to be online because of the time difference. I have been sorry. Stop sharing. I have been trying to keep up my scheduling my program with the conference, but it was very difficult. So that was my presentation. Thank you very much, everybody, and I wish we could meet physically one day with many of you. Have a nice rest of the day in the conference and enjoy the conference.
Thank you so much, Dr. Modias, to share your research about the impact of agriculture, the challenges you are facing now, and also to talk about food security, sustainable resource management, energy consumption, food quality and safety, so climate change. So Dr. Rodias talked about his recommendation, including precision farming, which were the utilization of sensors, agri-robotics, and, for example, grass pots that help farmers manage crops and soil with greater accuracy, improving yields and reducing waste. So it makes more effective and efficient. We really hope that this kind of technology can be adapted in Indonesia. Okay, ladies and gentlemen, as we come to the end of the first session, I would like to express once again my sincere gratitude to Professor Ahmad Yunus and Dr. Rodias for sharing your valuable expertise and research with us today. Your contributions to the field of agricultural innovation are truly inspiring. So we hope today's webinar has provided you with fresh perspective and ideas on optimizing agriculture and ensuring sustainability in the agri-food sector, especially in the climate change process. Thank you all for joining us, and we look forward to seeing you at our future event. Have a great day, and now I hand the event back to the Master of Ceremony.
All right. Thank you, Ms. Rufida, Professor Yunus, and Mr. Rodias for bringing us to a very productive and interactive session today. And ladies and gentlemen, we love to say thank you very much for the first sessions of Talk Show this morning. Thank you for the moderator today, and also the speakers for the insightful knowledge. Before continuing with this next session, we will be right back soon after the following video. Stay tuned for the next session and would join with us our next speakers, Professor Sajib Kumar Panda and Professor Harry.
The world faces a significant global challenge as the human population is projected to reach 9 billion by 2050. Food security ranks among the most urgent international issues. The COVID-19 pandemic has further strained health systems worldwide. Fossil fuels, predominant in electricity production, emit greenhouse gases that exacerbate climate change. The last decade has been the warmest ever recorded, leading to devastating climate disasters. It is necessary to accelerate the transition to an affordable, reliable, and sustainable energy system by investing in renewable energy and implementing environmentally friendly energy technologies. Universities are pivotal in advancing global welfare. ICSAE-XI, as a higher education institution, has become the common thread holding together all solutions for the 17 Sustainable Development Goals through its learning, research, and community service programs. ICSAE-XI was established on March 11, 1976, as one of the most outstanding universities in Indonesia. ICSAE-XI has built its vision and strategic plan on becoming an internationally excellent center of development in science, technology, and arts based on the noble values of national culture. ICSAE-XI is located in the city of Surakarta and is also known as Solo. Solo is a very comfortable city where Javanese culture and modern life blend. The Solo life, which upholds the value of harmony, has prepared ICSAE-XI graduates to be future leaders. To achieve the vision of Indonesian higher education, ICSAE-XI offers a variety of courses on a wide range of subjects conducted by 14 faculties, a vocational school, and a graduate school. With its adequate and appropriate learning infrastructure, ICSAE-XI offers a unique and engaging learning environment. It provides integrated IT facilities and information systems in a convenient academic atmosphere and green campus area. In addition to being a center of excellence, ICSAE-XI is home to students from all 38 provinces in Indonesia and 34 countries worldwide. This campus life creates a multicultural environment that promotes mutual understanding. Embracing diversity and respecting all cultures makes every student feel recognized and valued.
We understand that the world is facing many problems nowadays and also challenges in the future. Therefore, Universitas 11 Maret present to the society for solving the problems and anticipating the future challenges by three main activities: research, education, and community services. The significant contribution of Universitas 11 Maret is not only in national level, but also international level. Our action result in the international recognition as indicated in many global university ranking system. Looking at its potential, Universitas 11 Maret is ready to build partnership with your institution to enlarge our contribution and strengthen our reputation in the global society.
Every year, ICSAE-XI deploys more than 1,000 students and more than 1,800 lecturers to the community service program, together with research activities from lecturers, to solve various problems in society. Regarding food issues, ICSAE-XI develops various plant varieties and climate and soil mapping with adequate laboratory facilities. To encourage the use of renewable energy, ICSAE-XI has a Center for Excellence in Lithium Battery Science and Technology and Electric Motorbike Innovation. ICSAE-XI implements UNS Green Campus governance through emission-free days, waste recycling programs, and dye-based solar panels to support sustainable environmental management. ICSAE-XI has been developing startup, business incubation, and entrepreneurship programs to eradicate poverty. In education, ICSAE-XI deploys around 1,800 students every year to carry out teaching programs in schools. And finally, to contribute to the health sector, ICSAE-XI has a nonprofit teaching hospital to serve the community. Effective partnerships and strong collaborations have become inseparable parts of Universitas-XI. Our international partnerships create ample opportunities for student and staff mobility in collaborative research and teaching activities. International collaboration helps to give a global perspective on learning to address global challenges while still functioning in a national environment based on potential and local wisdom.
Together, we can solve the global problem. Together, we can anticipate the future challenge.
We gladly welcome you to explore and experience our program and enjoy our campus life, which depicts a blend of cultural power, professional life, and technological advancement. Universitas-XI. The world faces a significant global challenge as the human population is projected to reach 9 billion by 2050. Food security ranks among the most urgent international issues. The COVID-19 pandemic has further strained health systems worldwide. Fossil fuels, predominant in electricity production, emit greenhouse gases that exacerbate climate change. The last decade has been the warmest ever recorded, leading to devastating climate disasters. It is necessary to accelerate the transition to an affordable, reliable, and sustainable energy system by investing in renewable energy and implementing environmentally friendly energy technologies. Universities are pivotal in advancing global welfare. Universitas-XI, as a higher education institution, has become the common thread holding together all solutions for the 17 Sustainable Development Goals through its learning, research, and community service programs. Universitas-XI was established on March 11, 1976, as one of the most outstanding universities in Indonesia. Universitas-XI has built its vision and strategic plan on becoming an internationally excellent center of development in science, technology, and arts based on the noble values of national culture. Universitas-XI is located in the city of Surakarta and is also known as Solo. Solo is a very comfortable city where Javanese culture and modern life blend. The Solo life, which upholds the value of harmony, has prepared Universitas-XI graduates to be future leaders. To achieve the vision of Indonesian higher education, Universitas-XI offers a variety of courses on a wide range of subjects conducted by 14 faculties, a vocational school, and a graduate school. With its adequate and appropriate learning infrastructure, Universitas-XI offers a unique and engaging learning environment. It provides integrated IT facilities and information systems in a convenient academic atmosphere and green campus area. In addition to being a center of excellence, Universitas-XI is home to students from all 38 provinces in Indonesia and 34 countries worldwide. This campus life creates a multicultural environment that promotes mutual understanding. Embracing diversity and respecting all cultures makes every student feel recognized and valued.
We understand that the world is facing many problems nowadays and also challenges in the future. Therefore, Universitas-XI Maret present to the society for solving the problems and anticipating the future challenges by three main activities: research, education, and community services. The significant contribution of Universitas-XI Maret is not only in national level, but also international level. Our action result in the international recognition as indicated in many global university ranking system. Looking at its potential, Universitas-XI Maret is ready to build partnership with your institution to enlarge our contribution and strengthen our reputation in the global society.
Every year, Universitas-XI Maret deploys more than 1,000 students and more than 1,800 lecturers to the Community Service Program, together with research activities from lecturers, to solve various problems in society. Regarding food issues, ICSAE-XI develops various plant varieties and climate and soil mapping with adequate laboratory facilities. To encourage the use of renewable energy, ICSAE-XI has a Center for Excellence in Lithium Battery Science and Technology and Electric Motorbike Innovation. ICSAE-XI implements UNS Green Campus governance through emission-free days, waste recycling programs, and dye-based solar panels to support sustainable environmental management. ICSAE-XI has been developing startup, business incubation, and entrepreneurship programs to eradicate poverty. In education, ICSAE-XI deploys around 1,800 students every year to carry out teaching programs in schools. And finally, to contribute to the health sector, ICSAE-XI has a nonprofit teaching hospital to serve the community. Active partnerships and strong collaborations have become inseparable parts of ICSAE-XI. Our international partnerships create ample opportunities for student and staff mobility in collaborative research and teaching activities. International collaboration helps to give a global perspective on learning to address global challenges while still functioning in a national environment based on potential and local wisdom.
Together, we can solve the global problem. Together, we can anticipate the future challenges.
We gladly welcome you to explore and experience our program and enjoy our campus life, which depicts a blend of cultural power, professional life, and technological advancement. ICSAE-XI. The world faces a significant global challenge as the human population is projected to reach 9 billion by 2050. Food security ranks among the most urgent international issues. The COVID-19 pandemic has further strained health systems worldwide. Fossil fuels, predominant in electricity production, emit greenhouse gases that exacerbate climate change. The last decade has been the warmest ever recorded, leading to devastating climate disasters. It is necessary to accelerate the transition to an affordable, reliable, and sustainable energy system by investing in renewable energy and implementing environmentally friendly energy technologies. Universities are pivotal in advancing global welfare. ICSAE-XI, as a higher education institution, has become the common thread holding together all solutions for the 17 Sustainable Development Goals through its learning, research, and community service programs. ICSAE-XI was established on March 11, 1976, as one of the most outstanding universities in Indonesia. ICSAE-XI has built its vision and strategic plan on becoming an internationally excellent center of development in science, technology, and arts based on the noble values of national culture. ICSAE-XI is located in the city of Surakarta and is also known as Solo. Solo is a very comfortable city where Javanese culture and modern life blend. The Solo life, which upholds the value of harmony, has prepared ICSAE-XI graduates to be future leaders. To achieve the vision of Indonesian higher education, ICSAE-XI offers a variety of courses on a wide range of subjects conducted by 14 faculties, a vocational school, and a graduate school. With its adequate and appropriate learning infrastructure, ICSAE-XI offers a unique and engaging learning environment. It provides integrated IT facilities and information systems in a convenient academic atmosphere and green campus area. In addition to being a center of excellence, Universitas 11 Maret is home to students from all 38 provinces in Indonesia and 34 countries worldwide. This campus life creates a multicultural environment that promotes mutual understanding. Embracing diversity and respecting all cultures makes every student feel recognized and valued.
We understand that the world is facing many problems nowadays and also challenges in the future. Therefore, Universitas 11 Maret present to the society for solving the problems and anticipating the future challenges by three main activities: research, education, and community services. The significant contribution of Universitas 11 Maret is not only in national level, but also international level. Our excellent result in the international recognition as indicated in many global university ranking system. Looking at its potential, Universitas 11 Maret is ready to build partnership with your institution to enlarge our contribution and strengthen our reputation in the global society.
Every year, Universitas 11 Maret deploys more than 1,000 students and more than 1,800 lecturers to the community service program, together with research activities from lecturers, to solve various problems in society. Regarding food issues, Universitas 11 Maret develops various plant varieties and climate and soil mapping with adequate laboratory facilities. To encourage the use of renewable energy, Universitas 11 Maret has a Center for Excellence in Lithium Battery Science and Technology and Electric Motorbike Innovation. Universitas 11 Maret implements UNS Green Campus governance through emission-free days, waste recycling programs, and dye-based solar panels to support sustainable environmental management. Universitas 11 Maret has been developing startup, business incubation, and entrepreneurship programs to eradicate poverty. In education, Universitas 11 Maret deploys around 1,800 students every year to carry out teaching programs in schools. And finally, to contribute to the health sector, Universitas 11 Maret has a nonprofit teaching hospital to serve the community. Active partnerships and strong collaborations have become inseparable parts of Universitas 11 Maret. Our international partnerships create ample opportunities for student and staff mobility in collaborative research and teaching activities. International collaboration helps to give a global perspective on learning to address global challenges while still functioning in a national environment based on potential and local wisdom.
Together, we can solve the global problem. Together, we can anticipate the future challenge.
We gladly welcome you to explore and experience our program and enjoy our campus life, which depicts a blend of cultural power, professional life, and technological advancement. Universitas 11 Maret. The world faces a significant global challenge as the human population is projected to reach 9 billion by 2050. Food security ranks among the most urgent international issues. The COVID-19 pandemic has further strained health systems worldwide. Fossil fuels, predominant in electricity production, emit greenhouse gases that exacerbate climate change. The last decade has been the warmest ever recorded, leading to devastating climate disasters. It is necessary to accelerate the transition to an affordable, reliable, and sustainable energy system by investing in renewable energy and implementing environmentally friendly energy technologies. Universities are pivotal in advancing global welfare. Universitas 11 Maret, as a higher education institution, has become the common thread holding together all solutions for the 17 Sustainable Development Goals through its learning, research, and community service programs. Universitas 11 Maret was established on March 11, 1976, as one of the most outstanding universities in Indonesia. Universitas Sebelas Maret has built its vision and strategic plan on becoming an internationally excellent center of development in science, technology, and arts based on the noble values of national culture. Universitas Sebelas Maret is located in the city of Surakarta and is also known as Solo. Solo is a very comfortable city where Javanese culture and modern life blend. The Solo life, which upholds the value of harmony, has prepared Universitas Sebelas Maret graduates to be future leaders. To achieve the vision of Indonesian higher education, Universitas Sebelas Maret offers a variety of courses on a wide range of subjects conducted by 14 faculties, a vocational school, and a graduate school. With its adequate and appropriate learning infrastructure, Universitas Sebelas Maret offers a unique and engaging learning environment. It provides integrated IT facilities and information systems in a convenient academic atmosphere and green campus area. In addition to being a center of excellence, Universitas Sebelas Maret is home to students from all 38 provinces in Indonesia and 34 countries worldwide. This campus life creates a multicultural environment that promotes mutual understanding. Embracing diversity and respecting all cultures makes every student feel recognized and valued.
We understand that the world is facing many problems nowadays and also challenges in the future. Therefore, Universitas 11 Maret present to the society for solving the problems and anticipating the future challenges by three main activities: research, education, and community services. The significant contribution of Universitas 11 Maret is not only in national level, but also international level. Our action result in the international recognition as indicated in many global university ranking system. Looking at its potential, Universitas 11 Maret is ready to build partnership with your institution to enlarge our contribution and strengthen our reputation in the global society.
Every year, Universitas Sebelas Maret deploys more than 1,000 students and more than 1,800 lecturers to the Community Service Program, together with research activities from lecturers, to solve various problems in society. Regarding food issues, Universitas Sebelas Maret develops various plant varieties and climate and soil mapping with adequate laboratory facilities. To encourage the use of renewable energy, Universitas Sebelas Maret has a Center for Excellence in Lithium Battery Science and Technology and Electric Motorbike Innovation. Universitas Sebelas Maret implements UNS Green Campus governance through a mission.
Ladies and gentlemen, welcome back to General Assembly, the 11th International Conference on Sustainable Agriculture and Environment 2024. The honorable participants, we are now in the last presentation from Professor Sanjeev Kumar Panda from Central University of Rajasthan of India and Professor Harry Utomo from Louisiana State University of the United States. This session will be moderated by Mr. Agung Irawan, PhD. But before we begin, let me introduce his short biography. Mr. Agung is a lecturer and a researcher of Vocational School of Universitas 11 Maret. He was studied his doctoral degree in Animal and Rangeland Science in Oregon State University of the United States. All right, without further ado, please welcome Mr. Agung. Time is yours.
Thank you very much for very nice introductions. Good morning, everyone, all the audience, and welcome to our second General Assembly today on 11th International Conference on Sustainable Agriculture and Environment. My name is Agung Irawan, and I'm honored to serve as a moderator for these sessions. In the first session, we have two prominent speakers presenting frontier research related to gene editing to increase rice productions, sustainability, and global food security through precision farming systems. And in these sessions, we'll have other phenomenal speakers that will share their recent idea with us, still related to sustainable agriculture community. As we are aware, agricultural sector continues to face challenges in sustainability, productivity, and resilience. To sustain our agriculture and environment, the role of biotechnology, especially related to molecular genetics and functional genomics, has never been more critical. And today, we'll be exploring how these cutting-edge fields are driving innovations and enhancing agriculture practices. For this topic, I'm delighted to introduce our distinguished speakers, Professor Sanjeev Kumar Panda from Central University of Rajasthan, India. In these sessions, we will have similar formats to the first sessions, so which is a 35 minutes presentation from speakers and followed by 15 minutes Q&A. Okay, cool. Now, I would like to invite our first Professor Sanjeev Kumar Panda.
Yeah, good morning.
Good morning, Professor Sanjeev. Good morning. Yeah. So, but before presentation can be begin, I would like to introduce a little bit about the profile of Professor Sanjeev. Professor Sanjeev is a biochemist and molecular biologist from the Department of Biochemistry, Central University of Rajasthan. His research is focused in the fields of plant molecular biology and functional genomics to understand the mechanism how stress signal transductions and develop stress resilience crop plants. Prof. Sanjeev uses functional genomic platforms mostly, along with the genetic engineering and genome editing technology to understand the stress response in the crop and plant model systems. Okay, as we now have Professor Sanjeev joining us live from India, we'll shortly begin these sessions. So, good morning, Professor Sanjeev. How are you doing today?
Yeah, I'm good. Good morning. And can you help me how to share the slides?
Oh, of course, yeah. Okay. Yeah, I think let me check if you already be a co-host for this session. Oh yeah, so I think you can, Professor Sanjeev, you can directly share your presentation material from your computers.
So do I need to share, right?
Yeah.
So if I don't see my desktop in that, that's no, the whole screen is there. I just want to share the. So I don't want to share the screen, right?
Oh, you want me to help you to share your presentation material?
Only presentation.
Oh, okay. So yeah. Yeah, I think you now can open your PowerPoint or something.
Because I'm not using this platform for a long time now. Only during COVID I was using it. So is my presentation visible?
I'm sorry, excuse me. Can you say that again?
Can you see my presentation?
Not yet. I can see your computer screens, but not your presentation. So I think now you can open your. your presentation material directly from your computers? Or if you can send me the material, your presentations, I can help you to open from my computers. But for that, you need to send your file. You can let me you. Excuse me, sorry. I will.
So should I send an email?
Hello, Prof. Sanjib. I'm sorry. Could you please send me the files from the direct? If you cannot, yeah, you can either open your PowerPoint file from your computers. You can share the screen, or if you have some issue with that, you can send files to me via the chat.
How do I send the file to you?
You can send from the chat platform, and there is wait.
So my file is open now.
Now it's open. Okay, so you can click on the shares menu.
There. Okay, I'm clicking it.
Yeah, click the share menu, and then that should be open your screen or presentation.
Can you see now?
Wait, not yet, but probably, yeah. No, I can see your presentation. Yeah, perfect.
I'm trying to make it full screen.
Okay. Okay, thank you, Professor Sanjib. Yeah, now I can see your presentation material. So you will have about 35 minutes of presentation, and I will remind you 5 minutes before the time is running out. Now the time is yours. Thank you.
You can see, right?
Yeah.
Yeah. So, good morning.
Good morning.
I was speaking about the differing stress tolerance or stress responses and stress resilience in cropland. We're a group working on abiotic stress tolerance and agricultural biotechnology. This is a brief bio of mine, discussing different areas of research on which I work and collaborations and different project grants which we are having. So, as we talk of sustainable development and we talk of environmental disasters or climate change, you can see the how climate change is all pervasive from agricultural affecting agricultural productivity and causing pollution, causing pandemic, causing floods. It's all pervasive, and the climate disaster or climate change era needs to be very well managed and controlled so that a sustainable agricultural production and food security is ensured. And in this slide, you can see that we are going to have huge water scarcity in the future years, and the position which we have been facing for all these years are going to be very, very difficult scenario, and the agricultural productivity is going down and down, and the biodiversity loss, soil degradation, and the future pandemics are all related to the climate change issues. So this is a scenario of global climate change, and you can see the drought scenario, which is around 34%. Expected flood is 19%, storms and soil salinity associated with drought, and numerous different issues which are challenges for the agricultural activity globally. And we are a group which is working on numeric stress or environmental stress, and especially drought and different kinds of metalloids and metals and metalloids, and actual agricultural problem or challenges are being addressed too. So what we need to have the strategies for addressing the global climate change effects on agricultural production. You can see we should have short-term goals, we should have mid-term goals and long-term goals, which can help in maintaining the agricultural production. And the short-term goal includes the smart agricultural management technologies, water-saving irrigation systems, well-resistant crop varieties, on which we are actually working on, soil preservation and improvements. And that the efficacy is possible by supporting water-saving technologies, improving irrigation water use efficiency, reducing yield losses, and enhancing crop resistance, reducing greenhouse gas emissions, which is a big challenge for most of the developing and developed nations. In midterm goals, we have got innovation agricultural solutions, feasible solutions for sustainable fertilizer production, and effectively reducing the impact of climate change on uncertainties on crops, including nutrient use efficiency. So our group is working on nutrient use efficiency, and we're talking about those things, and establishing sustainable closed loop systems and adaptive management strategies that should be the long-term goals that will help in achieving efficient resource recycling and promoting sustainable agriculture. So coming straight to my area of research, and the lecture is mostly going to happen on this area. We are a group working for last almost 3 decades on plant microbiology, biochemistry, physiology, and we use functional genomic platforms and genetic engineering and genome editing technologies to address the biological questions, the bigger biological questions which will be addressed only at the global gene expression scale, and the functional genomics strategies like transcriptomes or RNA sequencing technology, next generation sequencing technologies, and metabolome analysis using LC-MS targeted and non-targeted metabolomics. We try to address the biological question in hand, and subsequently through molecular building, we try to into the crop plant, which could be climate smart plants or climate smart part of the climate smart agriculture. So there are PhD students or master students who are attending this program. We can focus on what is stress and any environmental condition that prevents the plants from achieving full genetic potential. And the stress signaling you can see in this slide, whether it is drought or heat, cold, or temperature stress, high temperature stress, or level stress, there is a signaling cascade involved, starting from the receptors in the plasma membrane or in the lysosol to the phenotypic plasticity that we see or physiological plasticity that we phenotype which we see at the end that goes through various or polycyclic aspects of signaling events, and our group work on understanding these upstream and downstream events and to identify critical genes and transcription factors which are responsible for giving these typical tolerance phenotypes so that the crop plants can be part of the sustainable agricultural system in the climate change era. So we work mostly on rice. Rice is the staple crop often for almost 50% of the world's population. And besides that, we also work on legumes, which are the rich source of proteins, especially in developing countries. So our group works on chickpea and mung bean, Vina radiata. So I'll be discussing a couple of things related mostly to rice. Some of the work considering the paucity of the time. You can see, and this is the whole the plethora of research which we work in the lab in collaboration with various international institutions of repute. So I will be discussing only a few things which are of importance. So I'll be talking mostly about the transcriptomic characterization of aluminum tolerance mechanism in rice and Viagra, which we are doing for almost last 20 years, 15 to 20 years with Japanese collaborators. We also work on the upland and lowland and aromatic and non-aromatic rice of Northeast India, which suffers from iron excess and drought. So that is in collaboration with the German groups. And we do a lot of work on microbiome, characterizing the microbiomes and how do they regulate the molecular mechanisms of that. So this is an overview of the work which we do. Now I come straight to the area of research which we are doing for the last 20 plus years. Starting with my first 21 years back, my first JSPS postdoc in Japan, I was introduced to aluminum research or aluminum research signaling in one of the national institutes for embryonic stress in the Okayama prefecture. So that was 21 years back, and we continued in collaboration with the Japanese and Americans and others to understand the real problem of soil acidity. So more than 30% of the world arable soil is acidic, and almost 20 plus years I worked in an area, northeastern part of India, where 90% of the arable soil or agricultural important soil are acidic. So the acid soil is just not the pH. It is related to pH or rhizotoxicity, phosphorus deficiency, calcium deficiency, magnesium deficiency, and manganese deficiency. Are you able to see the slide?
Yeah. Yes, we are able to see the slides, but now your slides is in at the first page of your slide.
Okay.
If you still have some presentation, you can continue.
Yeah. Can you see the slide?
Okay.
Now?
Yeah. Perfect. Now, yeah.
Perfect. Yeah. So soil acidity. So I'm talking about soil acidity, where aluminum is the third most abundant metal in the Earth's crust, and when the pH level goes down to 4.5 to 5.5, aluminum becomes toxic. So this toxic causes almost it affects more than 50% of the crop productivity. In northeastern India, like most of the Southeast Asian countries, the rice is the most important staple food, and the rice productivity is affected because of the soil acidity, which is 90% of the soil is acidic. It's not acting to the natural average. So we look into a high throughput functional genomics approach to understand what are the critical factors, what are the critical genes or mechanisms that exist in indica rice, especially, and its response to aluminum. So I would be, we have been working for a very long time, and these are some of the papers and books which we published in very prestigious journals, understanding aluminum stress signaling, and so the important part in aluminum stress result is with very fraction of minutes, the root growth inhibition is inhibited in presence of aluminum, and that in turn induces lots of physiological and biochemical changes and molecular changes in the cell. And it is not the root effect or the elongation zone, but the aluminum targets the distal transition zone of the root, and all that happens in the distal transition zone. Globally, all research is focused on understanding that. So there are a few in molecular aspects. There is a master regulator called sensitive to proton toxicity 1, STOP1. Sensitive to proton toxicity 1 was also discovered and published in Proceeding Natural Academic Sciences by my collaborators, journalist collaborators. While characterizing the obnoxious mutants. So the background of aluminum stress sensing and signaling and molecular regulation depends on this master regulator, which regulates any downstream genes like organic acid efflux regulators. So what happens in the root? Many organic acid transfers are there, and these organic acids are produced in the root, which selects aluminum and detoxifies aluminum. So externally and internally also in the vacuolar membrane, there are different kinds of transporters which help in sequestering aluminum or putting aluminum into the vacuole, and so that aluminum toxicity is basically not sensed. So these are some of the background work in the model systems, Arabidopsis, and in some crop systems. Based on that, we looked into the functional genomic aspects by high throughput phenotyping. This was one of the platforms which we used for understanding the natural genetic variation that is existing in the genotypes and the landraces of rice, which are grown in the area. So the localized approach, aluminum is a global problem, a national problem, a regional problem. So the localized agricultural problems need to be addressed. Approach genetic or population genetic approach would help us in understanding what is the mechanism. Types of some varieties, some languages are naturally tolerant and some are sensitive. So through these hundreds of varieties, hundreds of genotypes were screened for aluminum, and that we identified contrasting lines. You can see the contrasting lines of rice and its response to 100 micromolar of aluminum. You can see that in the sensitive geometry line, the root growth is heavily reduced, whereas in case of tolerant lines, the root growth is not affected that much, and that has been also characterized using different kinds of markers like aluminum induces catalytic accumulation and localization of aluminum ions, which was very different in these contrasting lines. We used the Illumina high-tech platform for RNA sequencing, and we got millions of these, and you can see RNA data processing pipeline which was followed for understanding its transcriptome. What is happening at the global gene expression level. We found out, if you see the gene heat map, we looked into the ortholog of STOP1, which is called ART1 in case of rice, that is aluminum resistant transcription factor, which is a STOP1 homolog. So I told you about the STOP1. Sensitive to proton toxicity 1, which is gene C2H2 gene finger transcription factor. So we looked into the genes which are downstream of ART1 and regulated by ART1 and also not regulated by ART1. So ART1 dependent pathway and ART1 independent pathways were looked into in the dysregulated genes expression, which was seen in case of tolerant and sensitive lines. So we found if you look at the heat map that shows ART1 related genes were upregulated by aluminum in at least one line, except few down-related genes. And 17 genes were classified in different gene clusters in case of tolerant and sensitive. I'll not go deep into the science. All these are listed in the papers, and you can look into the Google in my papers, and you can have a better understanding if you are interested into this area of research. So we looked also the expression patterns of in the various tissue of right, and using expression and expression of ABC negative phytase and beta glucosylate. We found these ABCs actually the carboxylate genes. We found these genes which are not dependent of ART1 conventional pathway. So these novel genes have been found to be very critical genes and new genes in indica rice varieties genome, which could be critical for further studying the aluminum stress or aluminum tolerance in rice. So we also looked into what is the mechanism of which the tolerant one is tolerant and sensitive one is sensitive. We did a co-expression network analysis and also looked at the promoter region of the differentially expressed genes. These differentially expressed genes, which are stress-regulated genes, looked into the switch diversity in the promoter region of the day. And very interestingly, we found there was switch diversity in the promoter regions of the tolerant lines as compared to the sensitive lines. We further looked into the events like alternate splicing, the genes which undergo alternate splicing. You know, alternate splicing is one of these molecular drivers for evolution. So, and many of the genes which are very known for stress regulations have those who have undergone alternative splicing. Only in the tolerant lines we found the alternative splicing event happening as compared to the sensitive lines. And also the previous slide, if you see the gene ontology, we found many of the cellular processes which are of our biological processes which are of importance starting from growth to the cell death process, which are related to aluminum stress earlier quoted, have been also been found in this global gene expression analysis. So considering these, we also characterized or validated using the important genes who should increase or who are heavily dysregulated, and that was a match with the INSS data. So the take-home message was of the paper was both ART1 dependent and independent pathways operating in indica aluminum tolerance. Many ART1 independent genes showing off-regulation ART is the carboxylate phytase is tolerant particularly and key to aluminum tolerance. And as I said about the switch diversity in the promoter region of the downstream genes, we see trans factor dependent aluminum responsive gene expression. And also, besides that, from more expression analysis, besides the enriched found in the promoter stage, and significant alternative splicing events observed in solvent cultivars under aluminum stress, suggesting aluminum tolerant cultivar reprogram the transcriptome both quantitatively and qualitatively in response to aluminum stress. And we further looked into another approach of metabolomics using LCM SMS, and we published in scientific reports. This paper is very interesting, and you can look into how metabolic changes, which is much downstream of the signaling events, is affecting in both sensitive and tolerant lines, and that mechanism, that is the mechanism that the reason behind the tolerance in case of the tolerant line this time as compared to the sensitive line. So we also looked into a very important gene which was earlier reported of importance for aluminum tolerance, that is aluminum use malic transporter gene. So this transporter helps in transport of malic acid, which is aluminum and detoxifies aluminum. We looked into a transgenic platform for developing, as you know, the legumes or coarse legumes are very notorious to the transformation, and this developing transit in legumes is very tough. So one of the projects we looked into whether heterologous expression of these important aluminum stress regulated genes can confer tolerance in blackgram. So develop a platform and generate a transgenic published this paper in plant biology years back, and we could find the transgenics are performing much better as compared to the divide guidelines. So I immediately come to another most important problem that the drought, as we see, Rajasthan, where I work, is not the western part of India, is a semi-arid and arid agro-ecosystem where the water is a big problem, and globally drought is the number one problem. As I said, 34% of problems related to drought only. So drought is a very big problem for the sustainable agriculture, and lots of preservation stages and mountain under drought stress. And our group has been working on, I will not talk about the drought stress signaling. We have been working for a long period on ABA dependent signaling, ABA accessibility, so which is a drought regulating hormone. So ABS dependent signaling and ABS independent signaling pathways are there, which have been very well regulated. And we looked into these ABS dependent and ABS independent signaling pathways in rice and how the drought is perceived in the vegetative state and in the mature state. So we looked into the terminal drought. What is globally happening, the terminal drought stage, right, and in the young developing seedlings. So we did a transcriptome analysis and published it in. So these are some of our papers on drought stress, which were published in excellent plant biology journals. And this is a work which I will be briefly speaking, which we published in Physiology recently this year, where we looked into one of the sensitive genotypes of aromatic rice, which is part of a consortium project for genetic improvement of scented rice. So we looked at the transcriptional networks that reveal late embryogenesis abundantly, regulating drought multiplication in aromatic rice. So using Illumina platform, we looked into the differentially expressed genes which are under drought stress. These, if you look at in the seedling stage, we compared both in seedling stage and in terminal mature stage, terminal drought stage, and you can see the number of bakes which are visible, or bakes are differentially expressed genes. Is much lower in case of developing stage as compared to the developed stage or mature stage. And among these, 58.3% were upregulated in stage, whereas it is 47.02% in mature stage. So if you look at the box plot which I showed, the box plot, if you see, you can see notably there is significant upregulation in the expression of gene families such as histotropin, LIA, P52, and rare code irreducible to genes which we earlier found out rare code irreducible to genes or gene family RCA25, 27 were seen, and also naturally the serine threonine protein kinases which are stress activated protein kinases, those are also seen in case of this experiment. This was also validated using qPCR analysis to validate the RNA-seq data. And this is the experimental design which we see in the developing and the mature stage report experiment. And a total of 9 upregulated genes we picked for qRT-PCR, and among them we looked at the LIA to develop the story, which is based on LIA and based on the rough signaling pathways. So the biological processes which were affected were significantly associated with abscisic and abscisic acid activated signaling pathways and negative regulators of activated signaling pathways. Many pathways associated with photosynthesis were also seen in case of under drought. So this is the Go into ontology analysis of the transcriptome. And the different metabolic pathways, stage analysis was seen, and you can see protein processing pathways in the recycling pathways in the endoplazmic reticulum, to galactose metabolism, Q10, suberin, water synthesis. Many of the pathways are affected, as you can see in the heat map. And this is the co-expression network analysis and WGCLA analysis, which are bit complicated to be explained in very brief. Please go through the physiology of paper, and you can have a good understanding. So what we wanted to see, wanted to tell co-expression analysis of Lia gene family only. Late embryogenesis about this protein family only revealed the DHL greater than 1, W118 as a major hub gene interacting with other genes, so that the story could be developed, which in turn co-express the threat responsive genes like ABI, ICSAE-XI, RCA2-5, 2-7, P2C, and CD3. These were all ABI dependent pathway genes. In addition, the presence of several abiotic stress regulatory genes suggested that drought stress is regulated by a large transcriptional gene network, particularly noted these awareness of Lia genes. So this approach has helped us in identifying the mechanism. The take-home message is that this the first time we did for the sensitive aromatic rice transcriptome and studied at molecular level the drought responses, and understanding these molecular dynamics is essential for bolstering plant resilience, as we are talking about sustainable agriculture through molecular breeding or through new breeding technologies like genome editing. The links which we have got from these approaches could be really translated and put into action, so that in very less time, climate smart or much lesser time, climate smart plants could be generated, which could withstand the future drought or future environmental changes. So this is the scenario of gene editing. We have got multiple Indo-German and other international projects and national projects on gene editing, where we do multiplex genome editing using different concepts of gene and different important layers for drought and for iron biofortification and iron excess studies. Our group is also working on quenching sustainable quenching hidden hunger, which is one of the sustainable development goals of the United Nations. So the hidden hunger is the lack of nutrients, appropriate nutrients, mostly in the Southeast Asian countries, which is seen in care of the lactating mothers and the children. So we try to biofortify the pulse legumes, like especially mung bean and chickpea, using gene editing approaches, understanding the iron homeostasis mechanisms, the molecular mechanism which is existing in plants. And that is one of the German projects which is running for a couple of years. So these are some of the genes which have been identified, and gene editing is in practice using these are some of the procedures, some of the protocols which we adopt, and I'll show you some of the real scenario, how we clone double gRNA or single gRNA, how we multiplex the guide RNAs and generate the gene edited lines. So these are some of the genes which we work on chickpea, and we also work on rice and mung bean. And these are some of these just duplex or some symbolic examples of how we work on genome editing. And these were the papers we earlier did with the pulse legumes. So we have got the capacity to generate transgenic or gene edited pulse legumes, mung bean or chickpea. So some of the PhD students are working now on mung bean, chickpea, and rice. And very routinely these transformational platforms, which you see embryonic callus in case of indica rice, which were transformed and cultivated with gene-edited constructs and gene-edited lines were generated. So these are the recognition pipelines for rice and mung, which is routinely practiced for generating the gene-edited lines which are tolerant to stress and also biofortified for a particular nutrient. So this is the platform of gene editing in chickpea where we use embryo chickpea embryo.
Excuse me, Professor Sanjay. I'm so sorry to interrupt you in the middle of your presentations, but because the time is almost running out, so could you please probably?
Yeah, I'm in the last slide. I'm in the
Thank
last
you so much. Thank you so much.
Almost finishing. So this is my group. This is the group of functional genomics and molecular biology laboratory, and these are the PhD students who are working on different aspects of stress and nitrogen use efficiency, genome editing, population genetics, and these are international collaborators from Germany, Japan, UK, Hungary, South Africa, where I serve as visiting professor and adjunct professor. And these are my national collaborators, and these are the funding agencies from Government of India and international funding from German German Academic Exchange Fellowship Exchange funding. So thank you very much.
Thank you so much, Professor Sanjeev, for a very interesting presentations. That was a very fascinating look how molecular tools such as transcriptomic, metabolomic, and many other tools were used to understand the stress response, drought stress in the plants, and to uncover and overcome such problem, and in order to unlock the full potential of plant productivity. And this is very relevant topic for especially for tropical agriculture as Indonesia. Again, thank you so much for the presentation. And now we, thank you so much. We have our second speakers, Professor Heri Utomo from Louisiana State University.
Are there any questions? I can take the question because I can take the questions if there are questions because I have to go to the university and the Indian time is 1.5 hour lagging. So
okay.
So if there are questions, I'll take the question and I can log out so that I can go to my.
Yeah, thank you. Okay, so before we move to the second speaker, if you have there is any question from the audience, please raise your hand, or you can. We have 5 minutes for Q&A with Professor Sanjeev.
Yes.
I don't see any questions in the chat column, so probably we can move to the next speaker. Again, thank you so much, Professor Sanjeev, for joining.
Thank you very much for inviting me for this wonderful international conference, and my regards to my friend Professor Ahmad, Professor Yunus, and I'm very happy to be associated with University Severus Merit again. And thank you very much. And I think I can log out, and I wish best of luck for your conference.
Thank you so much. Thank you. We'll, of course, if any audience or participant in this conference have any questions, probably feel free to send an email directly to Professor Sanjeev. I believe he'll be very happy to answer questions or something. Thank you so much. Thank you. Okay, thank you so much. Now we will move to second speaker of our session, Professor Heri Utomo from Louisiana State University. Let's check if Professor Heri already joined us today. Oh, yeah. Good morning, Professor Heri. Good morning. Can you hear my?
I can hear you. Can you hear me?
Yeah, I can hear you well now. Thank you so much for joining us today in our conference.
Right.
So I will, before the presentation begin, I will briefly introduce Professor Harry. Professor Harry is a professor at LSU-X Center, specializing on molecular genetics and plant genomics related to rice. So most of his research are focused on rice, and it is very interesting to see how the situations of research of his research in the United States, especially in the Louisiana State University X centers, about molecular genetics and plant genomic fields, and yeah, about especially about yeah that fields. Okay, Perry, how are you doing today in California?
Yeah, I'm in California right now in Los Angeles.
Okay, yeah. I know now is evening. Yeah, good evening. Yeah, California. It is night.
Yeah, tonight at 8 o'clock. So yeah,
Oh, okay.
like 10, 14-hour difference.
14-hour difference. Yeah, I still remember. I just returned from one that has the same time zone with California.
Yeah.
Okay, Prof. Harry, thank you so much. I'm honored to serve as moderator in your session.
Okay.
So without further ado, because the time is already late a little bit, so you can start your presentation. You will have 35 minutes as well for the presentation, and we will continue with Q&A for about 10 minutes. And now the time is yours. Thank you.
All right, thank you so much. I'm happy to be here to share what I know, what my research is, and stuff like that. And I'm delivering my lecture here from hotel room. So this is the hotel thing. So it's not from my office or house. So I've been in California since yesterday. I have a meeting with the Consular General in here this afternoon, and then moving on to the conference right here. I'm happy to do it. What I'm trying to do today in Indonesia, is try to give you in a simple way, in the concept, so that way anything that is a little bit more important can be catch that way. Otherwise, it's going to be very complicated, and I'm afraid with the online sometimes. The voice is not good enough, so it's kind of confusing to deliver the messages. So that's what I'm trying to do right now, to simplify everything, to make sure my concept or what I'm talking about can be understood correctly. And if you are having like a question, don't be afraid. You can stop me at any time, so I can referring to and resolve the thing that need to be understood clearly by audience. And the second thing is that I have difficulty with my computer. So in terms of the camera, but my presentation is in my computer. So I will switch into my computer because I cannot use both in my room, usually interfere to one another. So let me turn on my computer, and then I will turn off my cell phone, okay? When I use the computer, you will not see me, but you can see my PowerPoint presentation. Would that be okay enough?
Yeah, of course.
Okay.
That will be perfect. Thank you.
Okay. Let me switch to my computer. So you will see somebody registering right now. Let's see. Open. Okay, is still running Zoom. Join with computer audio. You let me join, then we'll see that. It's okay, and then I will share screen. Let's see. The audio has to be on. Can you unmute my audio? The host. Okay. So, can you unmute my computer? Can you see it?
Yes, you can see the presentation now.
Okay, good. So I will turn on my cell phone, okay?
Okay. And we can also hear your voice very clear.
Okay, that's great. That's good sign. A second. So maybe turn it on. All right. Can you still hear me?
Yes.
Okay. Just
Yeah, go ahead. Thank you.
All right. Okay, this is my first page. Can you hear it? Can you see it, right? Okay.
Yes.
How about my voice? Is it good? I cannot.
It's good.
I
It's
cannot
perfect.
hear you. So.
Yeah, it's perfect.
But as long as you can hear me for now, it should be good. And then if later on I will try to figure out how to. Oh, okay, right here I can crank it up. Okay.
Okay. Can you
All right.
hear me as well?
Yes, now I can hear you.
Okay. Thank you. Yeah, you can
So
go ahead.
This is the title of my presentation today. So the title is How Simple Genetic Modification Can Be Used to Drive Eco-Friendly Sustainable Agriculture. So I try to put my discussion around the topic of the conference, okay? So this is what I come up with, something that's simple, something that everybody can comprehend it easily, so that way the concept and the objective can be understood correctly. All right. For anyone who don't know me yet, my name is Heri Utomo. I'm the professor at the Rice Research Station, Louisiana State University, located in Baton Rouge, Louisiana, so next to Texas. All right. So why is it so important to achieve sustainability? There are three, at least, okay, not only three, but more than three, but I will put the most important one in here, at least three reasons why is it so important to achieve sustainability. Of course, the first one, the most important one, is to enhance human well-being. As we know that we are the main reason for being sustainable, because if the agriculture is sustainable, then our life would be much better. So sustainable practices promote healthier ecosystem, cleaner air, and of course, finally, promote better quality of life. Our lives getting better and better, as we can see, if we compare it to maybe our grandparent or grandparent earlier. So my life is getting better and better because of our understanding about the ecosystem, sustainability, and also, of course, the science. And then the second reason would be preserving resources. It's very crucial because agriculture can only be produced through sustainable cycle. If the cycle is not right, if the cycle is stopping, then there is no sustainable, there is no life that can be supported, because this is very important. Even though our technology advancing real well, even though our rocket can arrive in Mars eventually, but if our food cannot be guaranteed, everything else will be stopped. Maybe human being will no longer survive. So this is very important. Preserving resources is not only for the love of our planet, but for the love of our life too. Because without preserving resources, there is no guarantee that production can be achieved appropriately. And then, of course, as we know that climate change happen all the time. I mean, throughout the history of Earth, happening many times, the climate disaster can happen anytime. So that's why in the small scale, we need to build climate resiliency, because we know that this is not guaranteed. The radiation from the sun is not always guaranteed that way. Sometimes it fluctuates, sometimes because we recklessly destroying the ozone layer, then the impact on the crop and us as well is going to be dramatically changed. So we need to maintain that balance. So that way we allow human being to be access for a longer time. So again, here I put 3 examples of strategies for achieving sustainability, the most important one. So I just want to concentrate on this one, on these 3, because this is the most important one, and I would like us to understand clearly what it takes to achieve the strategy, to make the strategy working. First of all, of course, is the efficiency of use of resources used. So this is by optimizing resource utilization in many aspects, including agriculture, industry, and our own daily life. So we are responsible for what we are doing every day. If we're conscious about that thing, if we are conscious about what we are doing and their effect on efficiency of resource use, we are contributing to achieving sustainability. So a little change in the way of our habit in life will have a dramatic impact on achieving sustainability. So this is collective responsibility that we need to understand. And of course, the second one is the renewable energy that doesn't cause ecological disaster, energy that is more efficient to produce, energy that is available without much effort or much cost of it. So this is something that everybody is doing it, including solar, wind, turbine, and kind of stuff, in addition to the typical gasoline or the motor gas. Okay, so transitioning to clean energy is one aspect of putting us into renewable energy more efficiently, and as also happening in our daily life, everything in circular. Our life is in circular motion, just like our planet circulating the sun. So everything is circulate and moving somewhere else while circulating. So the economy has to circulate to develop, to improve, or to decline. Yeah? So this circular economy has to be maintained so that way more productive, more efficient, minimize waste, and promoting recycling. Okay, this is part of the circular economy that we need to establish to make it better and better. Everyone has the responsibility to do it, so that we collectively can have a big impact on it. So achieving sustainability is essential for thriving planet and human being. We know if we don't do this, I mean, in the past, because we don't know, we don't have enough knowledge of enough science to understand it, all the great civilization suddenly gone because there is no sustainability around it. Because at that time, maybe in the Egyptian era or in the Inca era, there is no such technology that can help us to do that. Now, hopefully, the technology is enough to get us achieve the sustainability for many, many years, many, many decades, many, many centuries ahead of us. So this is very important. So in this theme, again, I would like to emphasize on something that's simple but has profound implication. Okay, the science of environmental sustainability and productivity is very, very complex. Indeed, it's complex. If it's not complex, it's not an environment. So environment is composed of so many different things moving all together, interact with each other. So it's become so complex. But in addition to the complexity, there is small thing that can cause so big impact. This is something that's very interesting that we can do, that we can use to protect us from inefficiency. So this is what my topic today is. So significant agricultural production and quality improvement actually can be obtained through a simple genetic mutation. So after all, the life is not only a pessimistic thing. The life is so exciting because, again, so simple, but so big impact of it. So looking at this possibility, so we know now that this is a promising avenue in addition to the complex thing. I'm not trying to make a complex thing to be simple. No, there is no way. But there is a simple thing that we can do to have high impact. Okay, this is what I'm trying to do, and then it can be used to improve crop resiliency, yield, and nutritional value. All of that without imposing additional burden on the environment. How beautiful would be, right? So easy, is so simple, but there is no additional burden to the environment. So that way, we can maintain with what we have right now, with what implication to the environment, but we got more yield, more resilient, and more nutritional value to it. How to do it? We will discuss that later on. So this is one example in selecting the semi-dwarf like 40, 50 years ago. Well, so basically the scientists looking at rice at that time is so tall, so long time to grow it. Once a year can be cut or harvested, and then he think that maybe if I can sort the plant out of it, make become semi-dwarf, semi short, it maybe will produce seed sooner. Yes, sure enough, it happened. So when the plant becomes shorter, it produces seed a little bit more, not a little bit, a lot of seed, because plant will signal it, hey, I'm at the end of the age, I'm almost dying, so I better produce a lot of seed so that way I can have a lot of progeny. So that's the survival mechanism kick in. That's why become more productive, less time to produce seed or yield, and then is not as vulnerable to the wind or to the storm, so that way it wouldn't lodge. By doing that, accidentally, the scientists produce yield that much bigger than before. That was creating green revolution because of one single gene, semi-dwarf SD1 gene. So this is very interesting in the past that we can also replicate for the future as example. This is a real example. So it's not like concept anymore, but this is the fact that's already happening. So from historical significance, the application of SD1, like I said, create green revolution from less production to much bigger fulfillment of the yield, so that way human being can reproduce more because it's enough food to go around. So it dramatically boosted rice production globally, and human largely avoided starvation around the world because of that. So it was like a theory that human population will be limited due to the lack of food, but actually with the green revolution there is no such limitation anymore. So that's why our planet now grew to approximately 8 billion people, the highest in the record of human history. But in addition, because the SD1 is so powerful, it's very difficult to replace it. This is something that we need to think about. If we don't think about it, then everything will be the same. When we have the same genetic, then is it vulnerable to anything like disease, like environmental disaster and stuff like that? So scientists still searching for the alternative of dwarf germplasm. Maybe you guys, the new generation of scientists, can find something new that can replace this, so that way the genetic diversity to the SD1 gene can be expanded, and the guarantee for long-term benefit can be fulfilled. Now, that's about yield, okay? We always thinking about if we have if we can eat enough food, we are okay. But actually, our body needed more than amount of food, but our body requires certain nutritional quality to it. It can be the same weight, the same amount, one cup rice. If it's eat more nutritiously, it will fulfill better into our health. So this is something that we need to think about. Not only the quantity of product, but also the quality, nutritional quality that is more important to it. So one example of that, in addition to rice, is high oleic acid soybeans. This is also simple mutation in a specific gene that create the oleic acid content in soybean oil increase. The implication would be was very impactful too. So the soybean oil resulted from this mutation has a healthier fatty acid profile, make it more desirable for consumer and food manufacturers. So this is open up all kind of food product that's that's healthier and more robust in nutritional quality. This is something that again demonstrate simple mutation can have high impact in nutritional quality. Another one is dealing with pest and disease resistance. One example is blight-resistant potatoes. If you recall that when we don't have this one, long time ago in Europe, many people starved because the potatoes production was destroyed by the Phytophthora infestan. It's very devastating disease, and because of that, there is no production or less production of potato. And many people depend on potato at that time, so many people died because of no potato anymore, not enough potato. And because of that, then scientists try to develop resistant potato to Phytophthora infestan, and they succeeded. And again, after that, then resistant potato can produce similar or more production of potato, and there is no need for chemical fungicide that will impact positively on the environmental pollution, and also reduce the production costs while maintaining high yield. Again, this is simple gene, but high impact, and the impact is not only for human being, but also for using less chemical, which is good for environmental. So again, this is something positive that we can do. I mean, individual of us, scientists around here in Indonesia too, can do the same thing. This is something that everybody can try and do something significant. Another real world example is like a rice variety with enhanced photosynthesis. So this is something that is also being developed right now. And the second one is tomatoes with extended shelf life, meaning that after the harvest, the tomato can stay in the room temperature in the supermarket for longer period. This is post harvesting mechanism, right? But it helped a lot because we can minimize food waste because it will not easily get rotten. So it will use for longer period of time. So that way will reduce the burden on the environment and maintain the production because it's still longer and you can use it longer. So that will help to stabilize the consumption and food production ratio. So this is something simple like this. You can think about it. You can improve it with the concept that you have. Then you can also contribute to something significant. The third example, the real one, is salt-tolerant barley. It's already released as variety. It can be cultivated in saline soil, salt soil. So making use of previously unproductive land by using this particular variety, and also reducing the use of freshwater irrigation need. Again, the impact is so profoundly good. Not only utilizing the soil that unutilized unutilizable last time, but also reduce the use of freshwater need. So this is something that again demonstrate how big was the impact. So I will not maybe repeat this one. Basically, same thing, just to give you some idea, different wording, different perspective, but basically the same thing. And we'll jump to my own research now. So that's my background and why. Well, that's what the reason I'm doing what I'm doing right now. So I'm interested in changing the function, the health effect of rice associated with low glycemic index to help people with diabetes and to help healthy people as well to eat better, to control weight and so on. Again, see, the effect is so profoundly many, not changing the glycemic index, not only for good for the diabetes people, but also help the healthy people to maintain weight. I will explain why. This is the this is the old data, 2018. So, but the trend would be increasing incidence of diabetes. So this is the lowest. This is the lower value than right now. Like right now in Indonesia, it was like 10.7. We know it's more than about 30 million people. So it's about like 10% of it, 30% of the population. In China, is 116 million. That's a lot of people right here globally that has diabetes, and diabetes is very costly in terms of the healthcare. So in the United States itself, or in Louisiana itself, it requires $5 billion annually. That's a lot of money to deal with diabetes. If we can tackle of this problem, say tackle 10%, not all of them. We already save a lot of money. BPJS can save a lot of money by applying this alternative. Okay. The one somebody who has diabetes, very familiar with this condition, so they know that the prolonged period of elevated blood glucose level can lead to cardiovascular disease, can create nerve damage or neuropathy, kidney damage, kidney failure, blood vessel damage, all kind of bad thing. Okay, so that's why doctor said, hey, avoid eating rice because rice usually high glycemic rice. So that's why when you have a high glycemic, you are not allowed to eat because it will create a problem. Your blood pressure will increase substantially, and it's very damaging to your health. So this is what my concern would be. If I can help this individual, I will be very happy and they can enjoy rice again. This is the typical rice in the market. It has glycemic index or GI value of around 73. When GI value of 73, it is said to be high GI food group. And what happens when you eat high GI food, it will create right here spike in the blood glucose level so quickly right here, because when the rice is digested in the stomach, it will absorb into the blood stream and previous one. So and then in the blood, insulin will be produced to convert the blood glucose into energy. If you are healthy, there is no problem, even though it is spiked like this. Okay, so spike like this, the insulin of your body will be produced and try to remove it as soon as possible, because the blood will be like sending messages, hey, we need to remove it, otherwise it's going to be bad to your health, like I mentioned in the previous slide. So the insulin produced and they remove as soon as possible because they don't want it to be longer in your blood stream. So a lot of insulin produced. Because of a lot of insulin produced, they work on removing and become energy. And then once they slowing down in terms of the glucose level, blood glucose level, the insulin is still there and still removing blood glucose from the bloodstream. And then it will cause right here, dramatic crash in here. So yes, we need to have blood glucose not zero, but we need some level to make it healthy. So our body has a measurement, not less than this one, not higher than this one. There is some limit in here. If it's less, your body will be tremble, will be weak feeling because there is no energy around. So that way, usually when you eat rice, normal rice, after eat and then suddenly remove the energy removed from your blood level, and then you feel like want to eat again. You want to snack. I'm still hungry. I need to eat, even though you just eat rice. This is where healthier people also suffer from. So they will eat more and create like obesity. So this is something that we need to avoid too. So this is my my current invention, high protein and low GI rice that has two distinct characteristics that is very important to our health. So this is side-by-side comparison between normal rice and low GI high protein rice right here. As you can see, the regular rice is spiking so much right here. The new rice, my rice, is lower in terms of releasing, but still longer. So that way your healthy body will feel like a lot of energy for a longer period of time. So this is something that can be achieved by creating low GI rice. Again, low GI rice means that rice is digested slowly and helping to stabilize blood glucose level. This is very important for diabetes. They don't need to be injected. Doesn't need insulin to be injected to their body. So they will reduce the cost of medication and also maintaining healthy balance of the glucose blood level. And then because of reduced risk of insulin resistance, particularly important for the individual with diabetes, and those also very important for healthy people who is trying to maintain their weight all along. Okay, this is the nutritional fact that is printed in the back of the back of the bag, so that way everybody can understand. Well informed what is they're eating. And this is the cuisine. Louisiana is very, 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 very interesting in Louisiana because their type of food is almost similar to Indonesia. Very spicy, rice based. So as you can see in here, this is our rice, and it's very pretty, white and nice, and can be blended to their cuisine right here, including etouffee and then jambalaya and all kind of stuff. So it's very adaptable to the local cuisine in here in Louisiana, and we are very happy with that. So this is the commercial production of the high protein, low GI rice. So we asked the commercial guys, and here is the Mike Frugier with the M&S Frugier Farm Corporation in Louisiana. So it's maintained commercially and packaged and sell in the supermarket. This is the production of the foundation seed. It's been patented, registered, and PVB. This is the number of patent number 14//943177. It was in February 2018 we obtained the patent, and then with PV, plant varietal protection, and then with plant introduction number 674794. So this is non-GMO. This is from mutational breeding, so there is no restriction on the commercialization. So the market right away adopted this product. This is
Professor Harry, I'm sorry to interrupt you in the middle of your presentations, but we almost running out of the time. And could you please speed up a little bit your presentation so we can move to the Q&A? Because also, yeah.
How many minutes I have left?
You will have like around 5 minutes, and then we'll follow by around 5 or 10 minutes question.
Okay, fine, very good.
Thank you.
I'm glad you remind me. Okay, I will
Thank
be
you.
quick. I wanted to discuss it, but then me just one-way direction. I like to both-way direction. Okay, so this is basically my write-up that saying the lowest GI in the world and highest protein content in the world as well. This is me in the field with all the testing and just very particular, very typical thing in plant breeding at the end of the season. All right, and this is the foundation seed from Frontier. Again, I'm very quick right now, okay, just to have more time to discuss. This is Frontier. This is the name originator that we use. So before we ask the commercial producer to do it, we have to have the foundation seed available. This is the commercial production of it, using the combine to harvest the seed and package it and send it to the supermarket. And this is using the airplane to spread the fertilizer and also spray the pesticide. Okay. Okay. I just cut it off because that's the main message to it. This is another company that deal with that, the Cahokia name the company. And this is the step-by-step. It's a elaborate process. I make it simple in here, 7 years of developing. And now we are at this stage, regional marketing. We are still struggling to be exported into different countries. We are working on Peruvian project right now to try to expand it to Latin America, South America. This is the lab that I have, very simple. I think Indonesia can have something like that. It's nothing fancy about it. It's just typical lab. So by using this lab, I was able to do all of that. This is what it looks like, the rice. It's been available in 500 grocery store. This is when you Google it and type Paris rice, you can see where the Paris rice is sold. This is the staggering diabetes cost in the America, right? $327 billion. I don't know how, I'm not ready to use it rupiah because it's so, maybe it's very high. It's $1 billion. And this is the advantage of using protein content in terms of our health and also the lifestyle of ourselves. Okay, malnutrition is one aspect that we want to deal with. We know that world is having a problem with malnutrition, including us in Papua and some other places in Indonesia. Okay, so its conclusion. So again, very simple. By simple genetic mutation, we can provide a powerful way to boost agricultural production. And then by leveraging natural induced mutation, we can create crop and livestock varieties that are more resilient, productive, and nutritious. So this is my message, and I already initiate, and I can see the effect of it. With that, I would like to close and be happy to entertain any question you might have. All right. Thank you so much.
Thank you so much, Professor Harry, for a very nice and interesting story about rice and about the the real contributions of the research that you did, that you have been doing for the community. Especially it is interesting to see how to produce such low glycemic index rice, and in the country that we thought that it's not in the tropical country like Indonesia, but it's very successful. And now we'll open the floor for the question. For the audience that have questions, please feel free to raise your hand and ask question directly to Professor Harry.
I can see here that somebody asked Elsa Dick Etayeb. Okay.
Okay.
Asking,
yeah, you can. Yeah.
I have one question. What is the percentage of protein of this rice variety? The percentage is 11% by weight. So if you eat like 100 grams, you will get 11 grams of rice of protein.
11% of protein by weight. To put in the perspective, how much protein contains in normal rice, Professor Terry?
Around 6%, 6-7%.
Around 6%. So it's pretty high for rice, and it's very
improved like 55% of the original. Again, this is without changing cultivation, without changing fertilization, anything that remains the same. Again, it demonstrates that without changing anything to burden the environment, we can add protein, pure protein from it.
And it was due to the genome mutations of the small gene of the SD1? Oh, okay.
Right. Yes. It's not SGI, but it's protein related.
It's protein. Yeah, it's due to
the height. Okay. Yeah.
Thank you so much. That's very interesting and very inspiring to us. And I believe that. So, and I have one question, Professor Harry. If nobody has questions in the forum, how about the acceptance and demand of this rice in the United States?
Okay, the demand is getting better. It's slow process because we have to educate, to inform people what is it good for. And in the U.S., unfortunately, rice in general, okay, outside Louisiana, Texas, and California, they don't eat rice. That's something that we have to understand. But the one who eat rice, they now understand the benefit, and we are open. I mean, like Facebook and everything else, they can comment on it. They can check their own blood glucose level, just like regularly. So they can, oh, my blood glucose level doesn't increase that much when I eat rice normally, something like that. So, and then somebody else will learn to it, and then, okay, let me try and stuff like that. So it's getting better and better every day, but still long way to go to make it publicly acceptable or consumed normally. So this is something that we need to do. Somebody asked me to turn on my cell phone so they can see my face, maybe.
Oh, okay, sure. Yeah, yeah.
Okay.
Thank you.
Yeah. Go ahead. While I'm turning on, I will answer question if you have.
Okay. Anybody else has a question for Professor Harry?
No one? Oh, you just want to see my face? Not
I think it's also because the time is almost it's Friday, and I think everybody most of us needs to go to the mosque to the Jumatan. So yeah, that's probably it's unfortunately it's very not. We hope to have more time to chat with Professor Harry about this very interesting. I just heard really about this as well. I used to live in Oregon. There are a lot of rice, but I'm not sure if there is any kind of rice like this. So this is very interesting and will help people, American people. That's also very concerning about about the diabetes issue in there. Thank you so much, Professor Harry. I really appreciate your time and to share your research, your idea, and your very inspiring story with us today. And for the audience, I also would like to thanks very much for still joining us at this time. And with that, I conclude this session. And again, you have a very wonderful day today to keep in the conference. We will continue after the breaks and the Master of Ceremony will have some announcement for you all. Thank you so much. And then I return the sessions to the MC.
All right. Thank you, Professor Sanjeev, Professor Harry, and Mr. Agung for bringing us to a successful and interesting session today. And once again, thank you so much for all the participants. Also, we have announcements for you. For participant certificates will be sent by the committee within a maximum of 3 days after the event. So please type your email carefully. And there is another announcement that we are moving on to the break time until 1 p.m. So for the participants, if you want to pray and have lunch, you can do it within the time, and the participants need to join the Zoom meeting at 1 p.m. for another parallel session. So ladies and gentlemen, this brings our program this morning to a close. Before we officially end, I would like to extend a heartfelt thank you to our speakers, moderators, and participants for your time and attention. We are optimistic that today's session will guide us toward a more sustainable future, especially in the field of agriculture. Your presence here is invaluable, and we look forward to working together towards a greener and healthier environment. I am Deandra Shirley, your Master of Ceremony. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.